Right now, as you sit reading this, you are moving through space at over 2 million kilometers per hour. Not because of Earth's rotation, which spins us at a comfortable 1670 kilometers per hour at the equator. Not because of our orbit around the Sun, which carries us at 107,000 kilometers per hour through the inner solar system. Not even because of the Sun's journey around the Milky Way, which accelerates our entire solar neighborhood at 720,000 kilometers per hour as we orbit the galactic center. No, you are being pulled towards something vast and hidden, a gravitational focal point so massive it influences the motion of 100,000 galaxies across a region of space 500 million light-years wide. This is the Laniakea Supercluster, and you live inside it. Most people have never heard this name. Most will go their entire lives without knowing their true cosmic address, content to think of themselves as residents of Earth, perhaps citizens of the solar system, maybe even inhabitants of the Milky Way galaxy. But your address extends much, much farther. In 2014, astronomers rewrote the map of our local universe and gave us a new home, a structure so enormous that it makes our galaxy seem like a single grain of sand on a cosmic beach. They traced the invisible rivers of gravity that flow through space, mapped the currents that carry galaxies through the universe like leaves floating on a stream, and discovered that everything we can see, every galaxy within hundreds of millions of light-years, belongs to a single immense structure bound together by gravitational flows. They named it Laniakea, from the Hawaiian words Lani meaning heaven, and Akea meaning spacious, immeasurable, or boundless. The full translation is immeasurable heaven, though some interpret it as open skies or spacious heaven. The name honours the Polynesian navigators who crossed vast oceans by reading the stars, using their intimate knowledge of the heavens to find their way across thousands of miles of open water. Just as those ancient voyagers navigated the Pacific by understanding the celestial sphere, modern astronomers navigate the cosmic ocean by reading the motion of galaxies, tracking their velocities and positions to map the invisible structure of space-time itself. The discovery of Laniakea represents one of the most significant breakthroughs in our understanding of cosmic structure. It revealed that the universe is organized on scales far larger than anyone had imagined, with galaxies flowing through space in coordinated patterns spanning hundreds of millions of light-years. It showed us that our galaxy is not drifting randomly through an empty void, but is part of a grand cosmic architecture, a web of matter and energy stretching across the observable universe. And it gave us a new perspective on our place in the cosmos, showing us that we are residents not just of a galaxy or a cluster, but of an immeasurable heaven that encompasses everything we can see, and more besides. If you are ready to discover your place in this immeasurable heaven, if you're ready to learn how astronomers mapped the invisible, to understand what lies at the heart of our supercluster pulling us inexorably forward, and to grasp the true scale of the cosmic web in which we are embedded, then hit that like button and subscribe. Because we are about to embark on a journey across 500 million light-years of space, through structures so vast they dwarf everything you thought you knew about the universe. We begin. Let me give you an address. Not your street address, not your city or your country or continent. I want to give you your cosmic address, the full coordinates of where you exist in the universe, tracing your location from the familiar to the incomprehensibly vast. This address will take us on a journey from the world you know to structures so enormous they challenge the very limits of human imagination. You live on Earth. That part is obvious, perhaps even banal, but Earth is already more than it seems. This blue marble spinning through space, with its 7 continents and 5 oceans, its 8 billion human inhabitants and its countless other forms of life, is itself a cosmic rarity. A rocky planet with liquid water on its surface, orbiting in the habitable zone of a stable star, protected by a magnetic field that shields it from deadly radiation, with a large moon that stabilizes its axis and creates the tides. Earth is precious beyond measure, and it is the only home we have ever known. But Earth does not exist in isolation. It orbits the Sun, completing one circuit every 35.25 days at an average distance of 140 million kilometers. This makes you a resident of the solar system, a family of 8 planets, dozens of moons, hundreds of thousands of asteroids and billions of comets, all bound to a single star by invisible threads of gravity. The Sun itself is a middle-aged yellow dwarf star, unremarkable in most respects but exceptional in one. It has remained stable for 4.6 billion years, providing the steady energy that allowed life to evolve on the third planet from its fire. The solar system, vast as it seems to us, is merely one tiny corner of something incomprehensibly larger. We sit about 2/3 of the way out from the centre of a spiral galaxy containing between 200 and 400 billion stars, each one a sun in its own right, many of them likely surrounded by their own planetary systems. You live in the Milky Way, a barred spiral galaxy roughly 100,000 light-years across, with 4 major spiral arms curving out from an elongated central bar. Our Sun resides in a minor arm called the Orion Spur, or Local Spur, nestled between the larger Perseus and Sagittarius arms. From our vantage point, about 27,000 light-years from the galactic centre, we see the Milky Way as a luminous band stretching across the night sky, the combined light of billions of stars too distant to resolve individually. Ancient cultures around the world wove myths about this celestial river, this road of stars. They did not know they were looking edge-on through the disk of their own galaxy, seeing the accumulated glow of countless suns scattered across tens of thousands of light-years. The Milky Way is not alone. It belongs to a collection of about 80 galaxies called the Local Group, bound together by gravity across a region about 10 million light-years wide. Most of these galaxies are dwarf galaxies, small sections of a few billion stars or less, but 3 dominate the Local Group by mass and size. There is our own Milky Way. There is Andromeda, designated M31, a spiral galaxy slightly larger than our own, located about 2.5 million light-years away. And there is Triangulum, designated M33, a smaller spiral about 2.7 million light-years distant. These 3 massive galaxies and their retinue of smaller satellites form a gravitationally bound system that will remain together indefinitely, even as the rest of the universe expands away from us. Andromeda deserves special mention. It is our largest neighbour, containing perhaps 1 trillion stars to our mere 200 to 400 billion. More importantly, it is hurtling toward us at 110 kilometers per second. This might sound alarming, and indeed it represents an inevitable cosmic collision. But we need not worry. The collision will not occur for another 4 billion years, long after the Sun has evolved into a red giant and consumed the inner planets, possibly including Earth. When the Milky Way and Andromeda finally meet, their stars will not collide. The distances between stars are too vast, but their gravitational interaction will scramble both galaxies, flinging stars into new orbits and triggering bursts of star formation as gas clouds slam together. Over the course of 1 billion years or more, the 2 galaxies will merge into a single giant elliptical galaxy. But that is a problem for the distant future. For now, the Local Group remains our immediate cosmic neighbourhood, a small family of galaxies drifting through the universe together. The Local Group itself is not isolated. It sits on the edge of something much, much larger. About 54 million light-years away, in the direction of the constellation Virgo, lies an enormous concentration of galaxies called the Virgo cluster. This is where our cosmic address begins to expand dramatically. The Virgo cluster contains over 2,000 galaxies, though the exact number depends on how you define membership, as the cluster has no sharp boundary. Some estimates place the count as low as 1/300 confirmed members, while others suggest up to 2,000 when including fainter dwarf galaxies and objects on the cluster's periphery. Either way, the Virgo cluster represents a significant step up in scale from the Local Group. Where our local family contains dozens of galaxies scattered across 10 million light-years, Virgo contains thousands packed into a region about 15 million light-years across. The composition of the Virgo cluster reveals the typical makeup of large galaxy clusters. About 58% of its members are spiral galaxies like our own Milky Way, displaying the characteristic pinwheel structure with arms of stars, gas and dust winding outward from a central bulge. Another 27% are elliptical galaxies, smooth, featureless collections of stars shaped like footballs or spheres, typically found in the densest regions of the cluster where galaxy collisions and mergers have scrambled spiral structures beyond recognition. The remaining 15% are irregular galaxies that defy easy classification, their shapes distorted by gravitational interactions with neighbours or by violent internal processes. Although spiral galaxies are more numerous in Virgo, the 4 brightest and most massive members are all giant elliptical galaxies. The most famous is Messier 87, designated M87, a supergiant elliptical galaxy containing several trillion stars. M87 sits near the dynamical centre of the cluster and is notable for several reasons. It contains one of the largest known supermassive black holes, weighing in at 6.5 billion times the mass of the Sun. This black hole made headlines in 2019 when the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow, a glowing orange ring surrounding the dark silhouette of the event horizon. M87 also displays a spectacular jet of plasma shooting out from the vicinity of the black hole at nearly the speed of light, visible in radio and optical images as a blue beam extending thousands of light years into space. The other bright ellipticals, including M84, M86, and M49, each contain hundreds of billions to a few trillion stars. M49 is the brightest member of the cluster in a visible light, while M87 is the most massive overall. These giant galaxies likely formed through the merger of many smaller galaxies over billions of years, growing by cannibalizing their neighbors in the dense cluster environment. The Virgo cluster's gravity dominates the local region of space. Its enormous mass, estimated at about 1.2 quadrillion times the mass of the Sun, pulls everything around it inward, creating what astronomers call the Virgo-centric flow. Galaxies within about 65 million light-years of the cluster center, including the local group, are being drawn toward Virgo at hundreds of kilometers per second. This motion is separate from cosmic expansion. It is a local gravitational effect caused by the cluster's immense mass. Our own local group is accelerating toward Virgo at somewhere between 100 and 400 kilometers per second, depending on how you measure it. This might not sound like much compared to the cosmic expansion velocities of galaxies billions of light years away, but it is significant. It means we are not simply drifting apart from Virgo due to the expansion of space. We are falling toward it, drawn by its gravity. Whether we will eventually crash into the Virgo cluster and be absorbed into that cosmic megalopolis depends on our exact velocity and distance. Current data suggests that we may be close enough and moving slowly enough that billions of years from now, long after the Sun has died, the local group could merge with Virgo, adding our modest collection of galaxies to its vast population. Though the uncertainties in these measurements mean this outcome is not certain. If such a merger occurs, by that time the Milky Way and Andromeda will have already merged into a single galaxy, so it will be this larger merged system that eventually joins Virgo, not the Milky Way as it exists today. The Virgo cluster, in turn, belongs to what was historically called the Virgo Supercluster or local supercluster. This was the largest structure astronomers could confidently define as our cosmic neighbourhood for most of the 20th century. It stretched about 110 million light-years across and contained roughly 100 galaxy clusters and groups, encompassing perhaps 47,000 galaxies in total when you count everything from giants like M87 down to the faintest dwarf galaxies. The Virgo supercluster was envisioned as a flattened disk with the Virgo cluster at its heart, surrounded by various smaller clusters and groups arranged in filaments and walls. Our local group sat on the outskirts of this disk, about 54 million light-years from the Virgo cluster center, near the edge of the structure. For decades, this was as far as our cosmic address extended. Astronomers could say with confidence we live in the Milky Way galaxy, part of the local group within the Virgo cluster's sphere of influence, belonging to the Virgo supercluster. That seemed like the complete story, the final chapter of our cosmic address. The Virgo supercluster represented the largest gravitationally associated structure of which we were a member. Beyond it lay other superclusters, scattered across the universe like islands in an ocean. But these were separate entities, distinct structures not connected to our own. Or so it seemed. But it was not complete, not even close, because the definition of a supercluster was vague, imprecise, based more on intuition and visual inspection than on rigorous physical criteria. When you look at the distribution of galaxies in space, you see a web, an interconnected network of filaments and clusters with no clear boundaries. Galaxies are not scattered randomly, but organized into long chains and sheets, like beads on string or stones in a wall. Dense clusters mark the nodes where multiple filaments intersect. Voids, vast nearly empty regions, separate the filaments. The structure is clear, but the boundaries are not. Where does one supercluster end and another begin? Where should you draw the line between structures that are connected and structures that are separate? Astronomers argued about this for years. Some define superclusters as high-density regions where galaxies congregate more thickly than average. By this definition, a supercluster is simply a big cluster of clusters, a grouping of galaxy clusters that happen to lie near each other in space. Others suggested different criteria, looking at the elongation of structures or the statistical correlation of galaxy positions. But none of these definitions were entirely satisfying. They were descriptive rather than dynamical. They told you where galaxies are located, but not where they are going, not how they are connected by gravity, not which structures are truly bound together by physical forces. The term supercluster was useful but imprecise, but more of a label of convenience than a rigorous scientific classification. Then in 2014, a team of astronomers took a completely different approach, and everything changed. Instead of looking at where galaxies are located, they looked at where galaxies are going. Instead of defining superclusters by density, they defined them by motion, by the flow of matter through space. They mapped the motion of thousands of galaxies and traced the flow patterns of gravity through the cosmic web. And what they discovered fundamentally changed our understanding of cosmic structure and our place within it. The Virgo supercluster, it turns out, is not a separate entity at all. It is part of something incomprehensibly larger. The whole structure we thought we understood, the 110 million light-year disk centered on the Virgo cluster, is actually just one appendage, one small component of a basin of gravitational attraction that dwarfs everything we had previously mapped. This larger structure contains not just the Virgo cluster and its satellites, but also the Hydra Centaurus supercluster, the Pavo-Indus region, the Southern supercluster, and numerous other groups and filaments scattered across an immense volume of space. It contains 100,000 galaxies spread across 500 million light-years. It has a mass equivalent to 100 million billion suns, or 10 to the 17th solar masses in scientific notation, and it has a name, Laniakea. Your cosmic address is not Earth, Solar System, Milky Way, Local Group, Virgo Cluster, Virgo Supercluster. Your cosmic address is Earth, Solar System, Milky Way, Local Group, Virgo Cluster, Laniakea Supercluster. The Virgo Supercluster that we thought was our home is merely one region within Laniakea, like a neighbourhood within a much larger city. And just as a neighbourhood shares infrastructure and connections with the rest of the city, the Virgo region shares gravitational flows with all the other parts of Laniakea. We are not residents of Virgo alone. We are residents of the immeasurable heaven. This is your home in the largest sense that has clear physical meaning. Everything you can see in the night sky, every star visible to the naked eye, every distant galaxy visible through our most powerful telescopes, all of it flows through this single vast structure. We are droplets in a cosmic watershed, falling toward a central gravitational valley along with 100,000 other galaxies, all of us carried by the same invisible currents of gravity. And at the heart of that valley, hidden behind a veil of dust and stars, lies something mysterious that has puzzled astronomers for decades: the Great Attractor. The story of Laniakea begins with motion. Everything in the universe is moving. On the largest scales, space itself expands, carrying galaxies away from each other in all directions. This is the Hubble flow, the cosmic expansion discovered in the 1920s. If expansion were the only thing happening, the motion of galaxies would be simple and predictable. A galaxy twice as far away would be moving away from us twice as fast. The relationship would be clean and linear, but it is not. When astronomers measured the velocities of nearby galaxies precisely, they found deviations. Some galaxies were moving slightly faster than expected, others were moving slower. Some were even moving toward us despite cosmic expansion. These deviations are called peculiar velocities. They represent the motion of galaxies due to local gravitational forces, separate from the overall expansion of the universe. Imagine a river flowing toward the ocean. That is cosmic expansion, the general current carrying everything forward. Now imagine leaves floating on that river. Leaves drift faster because they catch an eddy. Others slow down because they encounter rocks. Those variations in speed are like peculiar velocities, local effects superimposed on the larger flow. For decades, measuring peculiar velocities was difficult and imprecise. It required knowing both a galaxy's velocity from its redshift, which is easy to measure, and its actual distance, which is much harder to determine. Redshift tells you how fast a galaxy is moving away from or toward you based on how much its light has been stretched or compressed. But redshift includes both cosmic expansion and peculiar velocity mixed together. To separate them, you need an independent distance measurement. Astronomers developed several techniques for their measuring distances. They use Cepheid variable stars, whose brightness pulses at a rate related to their intrinsic luminosity. They use type Ia supernovae, which have a consistent peak brightness. They use the Tully-Fisher relation, which connects a galaxy's rotation speed to its intrinsic brightness. Each method has uncertainties, and distance measurements are always challenging. But by the early 2000s, astronomers had accumulated enough data to attempt mapping the peculiar velocity field of the local universe. The effort was led by Brent Tully of the University of Hawaii, along with collaborators Hélène Courtois from the University of Lyon, Yehuda Hoffman from the Hebrew University of Jerusalem, and Daniel Pomered from CEA Université Paris-Saclay. They assembled a catalogue called Cosmic Flows 2, which contained distance measurements for more than 8,000 galaxies within about 300 million light-years of Earth. For each galaxy, they subtracted the expected Hubble flow velocity based on distance and were left with the peculiar velocity, the galaxy's deviation from pure cosmic expansion. These peculiar velocities were not random. They showed clear patterns. Galaxies in certain regions were all moving in similar directions, as if being pulled by invisible hands. The team used these velocity measurements to reconstruct the gravitational field of the local universe. Gravity creates flows, matter attracts matter, and galaxies fall toward concentrations of mass. If you can map how galaxies are moving, you can infer where the mass concentrations are located. The technique is similar to how water flows in a landscape. Water runs downhill toward valleys. If you trace the streams, you can map the topography even if the land is hidden by fog. The Cosmic Flows team traced the streams of galaxies flowing through space. They looked for places where the flows converge, where many streams pour into a single valley. They also looked for places where flows diverge, where streams split apart as if flowing over a ridge. In hydrology, the boundary between two watersheds is called a divide. Water on one side of the divide flows into one river system. Water on the other side flows into a different system. The Cosmic Flows team applied the same concept to galaxies. They traced the divides, the surfaces in space where the gravitational flow changes direction. Inside one of these surfaces, all the galaxy motions point inward after removing cosmic expansion. Outside the surface, galaxies flow toward different attractors. They defined a supercluster as the volume enclosed by such a surface. It is a basin of gravitational attraction, a region of space where everything is being pulled toward a common center. This approach was revolutionary. Previous definitions of superclusters focused on density, on where galaxies cluster together. But density alone does not tell you which galaxies belong to a coherent structure. The velocity-based definition reveals the true boundaries, the limits of gravitational influence. When the team applied their method to the Cosmic Flows 2 data, they found that the Milky Way sits within a vast basin of attraction, extending 500 million light-years across. The Virgo cluster is part of this basin. So is the Hydra Centaurus region. So are dozens of other clusters and groups previously thought to be separate entities. All of them are flowing toward a central gravitational focal point located in the direction of the constellation Centaurus and Norma. The structure was so large and so well defined that it deserved a name. Noah Napoleon, an associate professor of Hawaiian language at Kapiolani Community College, suggested Laniakea. In Hawaiian, Lani means heaven, and Akea means spacious or immeasurable. Laniakea, the immeasurable heaven. The name honors the Polynesian navigators who used their knowledge of the heavens to explore the Pacific Ocean. Just as they charted their course by the stars, astronomers chart the course of galaxies through the cosmos. The name is poetic and fitting. We live in an immeasurable heaven, a structure so vast it challenges human comprehension. The discovery was announced in the journal Nature on September 4, 2014. The paper included stunning visualizations showing the flow of galaxies through Laniakea, like water streaming toward a drain. Streamlines traced paths through space, all converging toward the center of the supercluster. An orange boundary marked the limits of the basin, the surface where inward flow stops and galaxies begin moving toward neighboring structures. The Milky Way appeared as a tiny blue dot on the outskirts of Laniakea, far from the centre but still within the basin. The discovery redefined our cosmic neighbourhood. We are not residents of the Virgo supercluster. We are residents of Laniakea, and Virgo is merely one component of that larger whole. The scale jumped from 110 million light-years to 500 million light-years. The population jumped from hundreds of galaxies to 100,000. Our cosmic address expanded dramatically. But the discovery also raised profound questions. What lies at the centre of Laniakea, pulling everything inward? How does this structure fit into the even larger cosmic web? And is Laniakea itself part of something bigger still? To answer those questions, we must journey to the heart of Laniakea and confront the mystery that has haunted astronomers since the 1970s. There is a place in space where astronomers fear to look, not because of what is there, but because we cannot see it. This region lies behind the plane of the Milky Way, hidden by clouds of dust and gas and the glare of billions of stars. It is called the Zone of Avoidance, and it conceals one of the most important structures in the local universe, the Great Attractor. The story begins in the 1970s, when astronomers were mapping the large-scale structure of the universe for the first time. They measured the redshifts of thousands of galaxies and plotted their positions in 3 dimensions. The expectation was that galaxies would be receding uniformly in all directions due to cosmic expansion. Small deviations might exist due to local gravity, but on average, everything should follow the Hubble flow. It did not. In 1973 and again in 1978, astronomers reported anomalies in the motion of nearby galaxies. Something was pulling them off course. By the early 80s, the evidence had become overwhelming. The Milky Way and other galaxies in the local region were not simply expanding away from each other. They were also streaming toward a particular direction in the sky at about 100 kilometers per second. This was not a small effect. It was a massive, coherent bulk flow affecting hundreds of galaxies across hundreds of millions of light-years. The direction of motion pointed toward the constellations Centaurus and Norma in the southern sky. But when astronomers tried to observe that region, they hit a wall. The region lies directly behind the galactic plane, the disk of the Milky Way, where stars, gas and dust are most concentrated. Looking through the galactic plane with an optical telescope is like trying to see through a thick fog. The light from distant galaxies gets absorbed by dust or drowned out by the light of foreground stars. About 20% of the extragalactic sky is obscured this way. Astronomers call it the Zone of Avoidance. It is not a real zone, just an artifact of our unfortunate viewing angle from inside the Milky Way's disk. But it hides a crucial part of the universe from our view. Alan Dressler, working at the Carnegie Observatories in California, gave the hidden mass concentration its name in 1987. He called it the Great Attractor. The name captured the mystery and power of the phenomenon. Something massive was out there, pulling on us, and we could not see what it was. Estimates suggested the Great Attractor had a mass equivalent to tens of thousands of galaxies. Its gravitational influence extended across an enormous volume of space. Every galaxy within several 100 million light-years felt its pull. But what was it? A giant galaxy cluster? A supercluster? Something else entirely? For years, astronomers tried to peer through the Zone of Avoidance using different wavelengths of light. Dust blocks visible light, but it is more transparent to infrared radiation. Radio waves pass through dust easily. X-rays reveal hot gas in galaxy clusters. By combining observations at multiple wavelengths, astronomers slowly built up a picture of what was hiding behind the zone. In the late 90s, surveys using infrared and radio telescopes identified a massive galaxy cluster called the Norma cluster, located in the direction of the Great Attractor. Norma contains hundreds of large, old galaxies packed into a relatively small volume of space. Many of these galaxies are colliding with each other, a sign of the cluster's high density. The collisions heat gas to millions of degrees, causing it to emit X-rays that can be detected even through the dust. Norma was clearly important. It was the most massive cluster in the immediate vicinity of the Great Attractor's proposed location. But was it the Great Attractor? Not exactly. Further observations in 2005 revealed something surprising. A team conducting an X-ray survey called the Clusters in the Zone of Avoidance project reported that the Great Attractor was not as massive as originally thought. The estimates had been inflated by a statistical bias called Malmquist bias. which causes distant bright objects to be counted more often than nearby faint ones. When corrected, the Great Attractor's mass dropped to about 1/10 the original estimate. More importantly, the team confirmed that the Milky Way was being pulled towards something even more massive beyond the Great Attractor. The Shapley Supercluster, located about 650 million light-years away, turned out to be the dominant gravitational influence in the region. We will return to Shapley shortly. For now, the key point is this: the Great Attractor is not a single object. It is not a monster galaxy or a black hole or a concentration of dark matter forming a singular lump. It is a region, a gravitational focal point where multiple large structures intersect. The Norma cluster is part of it, so are the Centaurus and Hydra clusters. Together with several other massive clusters and filaments, they form what astronomers call the Great Attractor region. This region also includes a massive wall of galaxies called the Norma Wall, or Great Attractor Wall, which stretches across hundreds of millions of light-years. The wall contains the Norma cluster along with other clusters including Pavo 2, Centaurus Crux, and others hidden in the zone of avoidance. Recent surveys using radio telescopes have revealed even more structure. The Vela Supercluster, discovered through observations of neutral hydrogen emissions, appears to be another major component hidden behind the zone. The Vela structures are located closer to us than Norma, but were detected only recently because the dust obscuration is so severe. The Great Attractor is not a thing, it is a ploy. It is the central valley in the gravitational landscape of Laniakea. All the galaxy flows within Laniakea converge there. Streamlines from the Virgo cluster point toward it. Streamlines from the southern regions of Laniakea point toward it. Streamlines from the outer edges hundreds of millions of light-years away curve inward and terminate in the vicinity of the Norma and Centaurus clusters. This is where the gravity of Laniakea is strongest. This is the bottom of the basin, and we are falling toward it at 100 kilometers per second. That velocity sounds terrifying. It translates to over 2 million kilometers per hour. At that speed, you could travel from Earth to the Moon in less than 7 minutes. But in cosmic terms, 600 kilometers per second is not unusual. It is a typical peculiar velocity for galaxies influenced by large-scale structure. And while we are falling towards the Great Attractor, we will never actually arrive. Because Laniakea is not gravitationally bound, cosmic expansion is pulling everything apart faster than gravity can pull it together. We are falling toward the Great Attractor, but the target keeps receding. It is like running on a treadmill that speeds up faster than you can run. You move forward, but never get anywhere. Eventually, dark energy will pull the Great Attractor region so far away that its gravitational influence will fade to nothing. We will stop falling toward it and instead drift away as cosmic expansion carries us in opposite directions. But that is billions of years in the future. For now, the Great Attractor dominates the gravitational landscape of our local universe. It defines the center of Laniakea. To understand Laniakea, you must understand the cosmic web. The universe is not a smooth, uniform distribution of galaxies scattered randomly through space. Instead, galaxies are organized into a vast network of filaments and walls surrounding enormous voids. This structure resembles foam or a sponge, with matter concentrated along thin surfaces and threads, while most of the volume remains empty. The cosmic web is the largest scale structure in the universe, and it formed through a process that began shortly after the Big Bang. In the infant universe, matter was almost perfectly uniform. Almost, but not quite. Tiny quantum fluctuations during the first fraction of a second created regions that were slightly denser than average, and regions that were slightly less dense. These differences were minuscule, about 1 part in 100,000. But they were enough. Gravity amplifies even tiny advantages. Regions that started slightly denser attracted more matter from their surroundings, making them denser still. This created a positive feedback loop. Dense regions collapsed under their own gravity, forming the first stars and galaxies. Meanwhile, under-dense regions lost matter to their denser neighbours, becoming increasingly empty. Over hundreds of millions of years, this process transformed barely perceptible variations into dramatic structure. The densest peaks collapsed into galaxy clusters containing thousands of galaxies. Moderate density regions formed smaller groups and individual galaxies. The underdense regions expanded into vast cosmic voids containing almost nothing. But the structure was not random. The pattern of density fluctuations in the early universe had a specific character. determined by the physics of the Big Bang and cosmic inflation. This pattern favoured the formation of elongated structures, filaments stretching across tens or hundreds of millions of light years. Where multiple filaments intersected, matter concentrated most strongly, forming massive galaxy clusters. Where filaments were absent, voids expanded. The result is the cosmic web. Think of it as the skeleton of the universe. Filaments are the bones connecting nodes, and the nodes are clusters where multiple filaments meet. Walls are flat sheets where filaments merge together. Voids are the gaps between everything else. Filaments can stretch for hundreds of millions of light years, sometimes even longer. The longest known filament, called quipu, extends about 400 million light years. Other massive structures include the Sloan Great Wall, nearly 1.5 billion light years long, and the Hercules Corona Borealis Great Wall, which may extend over 10 billion light years, although its existence remains debate. The cosmic web is not just a visual pattern, it has physical significance. Filaments are highways for matter flowing through the universe. Dark matter dominates the mass of filaments, forming the gravitational framework. Baryonic matter, the normal matter made of protons and neutrons, flows along the dark matter filaments like water flowing through channels. Galaxies form where gas accumulates in the deepest parts of the filament potential wells. About half of the baryonic matter in the universe resides in these filaments, not in galaxies. It forms a warm, hot intergalactic medium with temperatures ranging from 100,000 to 10 million degrees Kelvin. This gas is extremely tenuous and difficult to detect directly, but it plays a crucial role in cosmic structure. It feeds galaxies, flowing down filaments and accreting onto galaxies at the nodes. It also connects galaxy clusters, creating bridges of matter spanning the voids. The cosmic web evolved over cosmic time. In the early universe, structure was subtle. Filaments were just beginning to take shape, and clusters were still assembling. As the universe aged, structure became more pronounced. Filaments grew more defined. Clusters grew more massive. Voids expanded and emptied out. Today, the cosmic web has reached a mature state, although it continues to evolve. Dark energy, the mysterious force accelerating cosmic expansion, is now beginning to dominate. Dark energy pushes space apart, working against gravity. In dense regions like galaxy clusters, gravity is strong enough to resist dark energy and keep the structure bound together. But on the scale of superclusters and filaments, dark energy wins. These structures are not gravitationally bound and will be torn apart over the next tens of billions of years. The cosmic web will gradually dissolve as expansion accelerates. Laniakea fits into this picture as one of many superclusters populating the cosmic web. It is a large structure but not unique. Other superclusters exist nearby, including the Shapley Supercluster, the Perseus-Pisces Supercluster, the Coma Supercluster, and the Hercules Supercluster. Each has its own basin of attraction, its own gravitational focal point pulling in surrounding galaxies. The boundaries between superclusters are not walls but watersheds. Galaxies near the boundary between Laniakea and a neighbouring supercluster experience a gravitational tug-of-war. The balance of forces determines which basin the galaxy belongs to. Move the galaxy slightly closer to one attractor, and it falls into that basin. Move it toward the other attractor, and it switches allegiance. The Milky Way sits near the boundary between Laniakea and the Perseus-Pisces supercluster. We are firmly within Laniakea's basin, but we are close to the divide. Shift our position by a few tens of millions of light years, and we might belong to a different supercluster entirely. This sensitivity to position highlights the dynamic nature of the cosmic web. It is not a rigid framework but a fluid landscape shaped by gravity. Galaxies flow through this landscape like water flowing over terrain, always seeking the lowest gravitational valleys. And the deepest valley in our region of the universe is the Great Attractor at the heart of Laniakea. Let us examine Laniakea in detail. What does this immeasurable heaven actually contain? How is it structured, and where do we fit within it? Laniakea spans approximately 500 million light-years across, although its exact size depends on how you measure it. The boundary is not a sharp edge, but a surface in velocity space where galaxy flows reverse direction. In physical space, Laniakea occupies a volume of about 2 million cubic megaparsecs. A megaparsec is 3.26 million light-years, so we are talking about an almost incomprehensibly large region. The supercluster contains roughly 100,000 large galaxies. This count includes all the major galaxies that contribute significantly to the gravitational structure. If you count smaller dwarf galaxies, the number would be much higher, potentially millions, but the 100,000 figure represents the galaxies we can observe and measure. The total mass of Laniakea is approximately 100 million billion solar masses, or 10 to the 17 solar masses in scientific notation. Most of this mass is dark matter, the invisible substance that dominates the gravitational landscape. Only about 15% is baryonic matter, the normal matter that makes up stars, planets, and everything we can see. Dark energy contributes to the total energy density but does not contribute to the gravitational mass. Laniakea is not a uniform blob. It has structure, subcomponents that were identified as separate entities before the 2014 discovery revealed they all belong to a larger whole. The Virgo supercluster is the most prominent component. Centered on the Virgo cluster about 65 million light-years away, it includes the local group and Milky Way. The Virgo cluster itself contains over 2,000 galaxies, including the giant elliptical galaxy M87 with its supermassive black hole. The Virgo region was historically called the local supercluster, and for decades astronomers thought this was our primary cosmic neighborhood. But Virgo is just one part of Laniakea, an appendage on the outskirts of the larger structure. The Great Attractor region forms the central valley of Laniakea. This includes the Norma cluster, the Centaurus cluster, and the Hydra cluster, along with numerous smaller groups. These clusters are among the most massive in the local universe, each containing hundreds or thousands of galaxies. Their combined gravitational pull defines the focus of Laniakea's basin of attraction. The southern supercluster is another major component. It includes the Fornax cluster, the Dorado group, and the Eridanus cloud. Fornax is one of the richest clusters in Laniakea, located about 65 million light-years away in the constellation Fornax. The cluster contains about 60 major galaxies along with hundreds of smaller ones. The Pavewindus telescopium region stretches across the southern sky, forming a filament connecting the outskirts of Laniakea to the central regions. This area was less well studied historically because it lies in the southern celestial hemisphere and was not accessible to northern hemisphere telescopes. But recent surveys have revealed it to be a significant structure in its own right. The Antlia wall and Fornax Eridanus structures add further complexity. These walls and filaments trace the edges of voids, regions where galaxies are scarce. The walls mark the boundaries between empty space and the concentrations of matter flowing toward the Great Attractor. All these components, previously thought to be separate superclusters or isolated clusters, are now understood as parts of a single coherent structure. They are connected by velocity flows, by streams of galaxies, all moving in coordinated patterns toward the common center. The Milky Way galaxy sits on the outskirts of Laniakea, far from the Central Valley. Specifically, we are located in the Virgo region, which itself is near the edge of the supercluster. If you imagine Laniakea as a giant basin with the Great Attractor at the bottom, the Milky Way is perched on the rim, high on the slope. We are flowing inward, falling toward the center, but we are at the periphery looking down into the valley from a distance. This position has advantages. Being on the outskirts gives us a better view of the overall structure. If we were embedded deep within the central regions, the density of galaxies would obscure our view. We could not easily map the flows or define the boundaries. From the edge, we can see both inward toward the center and outward toward neighboring superclusters. Our view is not perfect. The zone of avoidance still hides crucial regions, but our position could be much worse. The structure of Laniakea is not static. Galaxies are in constant motion, flowing along filaments, accreting onto clusters and responding to the gravitational landscape. Over time, this motion will redistribute mass. Clusters will grow more massive as they capture more galaxies. Voids will expand as matter drains away. The Great Attractor region will continue to accumulate mass, at least for a while, but the overall structure of Laniakea will not last forever. Because the supercluster is not gravitationally bound, dark energy will eventually overcome gravity and tear the structure apart. Clusters that are gravitationally bound, like Virgo or Norma, will survive. But the connections between clusters will break. The filaments will dissipate. The coherent flow toward the Great Attractor will reverse as expansion carries everything apart. Billions of years from now, Laniakea will no longer exist as a distinct structure. It will have dissolved into the expanding universe, leaving behind only isolated clusters and groups separated by ever-growing voids. But for now, in this epoch of cosmic history, Laniakea is real and well-defined. It is our home in the immeasurable heaven, the largest structure we can claim to belong to in any meaningful sense. And we are not alone in this cosmic basin. Recent discoveries suggest that Laniakea itself might be part of something even larger. Just when you thought your cosmic address could not get any more expansive, the universe delivers another revelation. Laniakea is not the end of the story. It might be just one component of a structure vastly larger still. The key to this discovery lies in an observation first made in the 1930s. Astronomer Harlow Shapley, working at Harvard College Observatory, was conducting a survey of galaxies in the southern sky using photographic plates taken in South Africa. He noticed an extraordinary concentration of galaxies in the constellation Centaurus. He called it a cloud, but it was unlike anything seen before. The concentration was immense, stretching across a huge area of sky with a distinctly elongated form. Shapley estimated its distance at about 231 megaparsecs, roughly 72 million light-years. This placed it far beyond the local group and Virgo, out at the edge of what could be observed with the technology of the time. For decades, the Shapley concentration remained a curiosity, a distant overdensity that did not fit easily into the emerging picture of cosmic structure. It was too far away to study in detail, and its relationship to nearby structures was unclear. But in the 1980s and 1990s, as redshift surveys mapped more of the universe, the Shapley concentration revealed itself to be extraordinary. It is not just a large cluster, it is a supercluster, one of the most massive concentrations of galaxies in the observable universe. The Shapley Supercluster contains dozens of rich galaxy clusters, spanning a region at least 260 million light-years across. Its mass is staggering, estimated at several times 10 to the 16 solar masses, making it one of the most massive structures known. And it lies in a very interesting direction. The Shapley Supercluster is located along the same general direction as the Great Attractor, but much farther away at about 650 million light-years. This raised an obvious question. Could Shapley be influencing the motion of galaxies in our local region? The answer is yes. Studies of galaxy velocities in the 1990s and 2000s revealed that the Milky Way and other nearby galaxies are not only moving toward the Great Attractor but toward Shapley beyond it. Shapley exerts a gravitational pull strong enough to affect galaxies hundreds of millions of light-years away. Its influence extends throughout the local universe, creating a large-scale flow that adds to the motion caused by the Great Attractor. In fact, some researchers argued that Shapley, not the Great Attractor, is the true dominant mass concentration in our region of the universe. The Great Attractor might be just a way station, a local maximum in the gravitational potential that galaxies fall into on their way toward the even deeper valley of Shapley. This idea remained somewhat speculative until recently, when improved data allowed astronomers to map the flow patterns with much higher precision. In 2024, the Cosmic Flows 4 catalogue extended the earlier work with distance measurements for over 56,000 galaxies. This massive data set allowed researchers to reconstruct the velocity field to greater distances, and with better accuracy than ever before, what they found was stunning. The basin of attraction centered on Shapley is enormous. It extends across a volume roughly 10 times larger than Laniakea, and based on the velocity field reconstructions, it appears to encompass Laniakea itself. According to recent analysis using the Cosmic Flows 4 data, there is approximately a 60% probability that Laniakea is not an independent supercluster, but rather a sub-basin within the larger Shapley basin. This interpretation suggests we are falling toward the Great Attractor, yes, but the Great Attractor, along with everything else in Laniakea, may itself be falling toward Shapley. The Shapley Supercluster lies at the centre of what some astronomers now call the Shapley Concentration or Shapley Attractor. This region acts as a gravitational sink for a vast surrounding volume, pulling in not just Laniakea, but also other nearby superclusters, including the Coma and Apus superclusters. If this picture is correct, then your cosmic address is even longer than we thought. You live in the Milky Way galaxy, part of the local group within the Virgo cluster, part of the Laniakea Supercluster, which is itself part of the Shapley concentration, and Shapley might not be the end. Some evidence suggests that the Shapley concentration is being pulled towards something even larger, a hypothetical structure sometimes called the Shapley Centaurus basin, but the data become uncertain at these distances. We are reaching the limits of what we can reliably map with current observations. The existence of structures this large poses challenges for cosmology. The universe is supposed to be homogeneous on the largest scales, meaning matter should be distributed uniformly when you average over large enough volumes. But Shapley and Laniakea are so massive and so large that they push the boundary of what is considered homogeneous. Some cosmological models predict that structures this large should be extremely rare, arising only through unusual fluctuations in the early universe. Finding ourselves embedded in one raises questions about whether the universe is as uniform as we assumed. Alternatively, these giant structures might be more common than the models predict, indicating that we do not fully understand structure formation. Either possibility is unsettling. We might live in an unusually structured region of the universe, which would violate the principle that our location is not special. Or our models might be missing some crucial physics that allows larger structures to form more easily. The debate continues. What is clear is that the local universe is more complex and more hierarchical than anyone imagined even a decade ago. Superclusters nest within larger superclusters, which nest within even larger basins of attraction. The cosmic web extends to scales far beyond what we can currently map, and we are just beginning to see the full picture. Understanding Laniakea requires understanding peculiar velocities. These are the key to mapping the cosmic web and defining the boundaries of superclusters. Let me explain how they work and why they matter. Every galaxy has two components to its velocity. The first component is the recession velocity caused by cosmic expansion. Space itself is expanding, carrying galaxies apart from each other. The expansion velocity of a galaxy depends on its distance. Farther galaxies recede faster according to Hubble's law. The relationship is linear. Double the distance, double the recession velocity. This is the Hubble flow, and it is the dominant motion on large scales. The second component is the peculiar velocity, the galaxy's motion due to local gravitational forces. This motion is independent of cosmic expansion. It arises because galaxies attract each other through gravity, creating flows toward concentrations of mass. Peculiar velocities are typically a few hundred kilometers per second, sometimes reaching over 1,000 kilometers per second for galaxies near massive clusters. To measure a galaxy's peculiar velocity, you need two pieces of information. First, you measure the galaxy's total velocity from its redshift. Light from a receding galaxy gets stretched to longer wavelengths, shifting toward the red end of the spectrum. The amount of shift tells you how fast the galaxy is moving away from us along our line of sight. Second, you measure the galaxy's distance using a technique independent of redshift. This could be Cepheid variables, whose pulsation period relates to their intrinsic brightness. It could be type Ia supernovae, which have a consistent peak luminosity. It could be the Tully-Fisher relation for spiral galaxies or the fundamental plane relation for elliptical galaxies. Each method has its own uncertainties, but they all provide an estimate of distance that does not rely on the galaxy's velocity. Once you have the distance, you can calculate what the galaxy's recession velocity should be due to cosmic expansion alone. Multiply the distance by the Hubble constant, and you get the expected Hubble flow velocity. Subtract this from the total observed velocity, and what remains is the peculiar velocity. This is the galaxy's motion relative to the smooth Hubble flow. Peculiar velocities are not random. If they were, they would average to zero when you look at large enough volumes. But they do not average to zero. They show coherent patterns, large-scale flows where many galaxies are all moving in similar directions. These flows trace the gravitational influence of massive structures. Galaxies fall toward overdense regions and flow away from underdense regions, creating a velocity field that mirrors the distribution of matter. Mapping the peculiar velocity field is like mapping the currents in an ocean. Some regions have strong currents flowing in one direction. Other regions have calmer waters or eddies. By tracing the flow patterns, you can infer where the sources and sinks are located, where matter is accumulating or being evacuated. The Cosmic Flows project has been compiling peculiar velocity measurements for thousands of galaxies. The first catalogue, Cosmic Flows 1, contained about 1 to 800 galaxies. Cosmic Flows 2, published in 2013, expanded to over 8,000 galaxies and provided the data that enabled the discovery of Laniakea. Cosmic Flows 3 and Cosmic Flows 4, published in subsequent years, pushed the sample to over 56,000 galaxies, extending the mapped volume to about 1 billion light-years from Earth. These catalogues are remarkable achievements. Each distance measurement requires painstaking observations, often with multiple telescopes and techniques to ensure accuracy. The uncertainties are carefully quantified, and the data are cross-checked against simulations to validate the reconstruction methods. Using this data, astronomers reconstruct the three-dimensional velocity field of the local universe. They use mathematical techniques from fluid dynamics and topology to trace flow lines, identify convergence regions, and locate divergent surfaces. The result is a map showing how galaxies flow through space like rivers flowing through a landscape. For Laniakea, the flow pattern is clear. Galaxies throughout the supercluster are moving inward toward the Great Attractor region after removing the cosmic expansion. Streamlines from the Virgo cluster curve inward. Streamlines from the southern regions bend toward the center. Streamlines from the outer boundaries hundreds of millions of light-years away all converge in the vicinity of Norma and Centaurus. The boundary of Laniakea is the surface where this inward flow stops. Beyond the boundary, galaxies flow toward different attractors. Near the boundary, the flows diverge like water flowing over a ridge. This is the watershed, the divide between basins of attraction. The Cosmic Flows team traced this watershed surface around the entire volume of Laniakea, mapping its shape in 3 dimensions. The resulting boundary is not spherical. It is irregular and elongated, shaped by the distribution of matter and the gravitational influence of neighbouring superclusters. In some directions, the boundary extends farther, because there is less competition from nearby attractors. In other directions, it terminates closer because neighbouring structures exert their own pull. The peculiar velocity field also reveals other features. It shows repellers, regions of underdensity from which galaxies flow away. These correspond to cosmic voids, large, nearly empty regions where the lack of matter creates an effective repulsive force. Galaxies on the edges of voids are pushed outward by the gravitational imbalance, flowing toward the surrounding filaments and clusters. One prominent repeller near Laniakea is called the dipole repeller, located in the direction opposite to the Great Attractor. Galaxies in that region are flowing away from the void toward denser areas, including Laniakea. The combined effect of the Great Attractor, pulling galaxies inward, and the dipole repeller pushing galaxies away from the opposite direction creates a strong dipole pattern in the local velocity field. Understanding these flows is crucial for cosmology. Peculiar velocities complicate efforts to measure the cosmic expansion rate because they add extra motion on top of the Hubble flow. When you observe a distant galaxy and measure its redshift, you see a combination of expansion and peculiar velocity. If you do not account for the peculiar velocity, your estimate of the expansion rate will be biased. This is particularly important for measuring the Hubble constant, the parameter that describes how fast the universe is expanding. Recent measurements of the Hubble constant from nearby supernova show tension, with measurements from the early universe disagreeing by about 9%. Some of this tension might be due to inadequately correcting for peculiar velocities. If we live in an unusual region with larger than typical peculiar velocities, our local measurements might not represent the global expansion rate. Laniakea and Shapley might be biasing our observations, making the universe appear to expand faster locally than it does on average. Think of the universe as a landscape. Not a physical landscape of hills and valleys, but a gravitational landscape where mass creates wells and voids create ridges. Galaxies move through this landscape like water flowing downhill, always seeking the lowest points. Laniakea is one of these low points. A valley in the gravitational potential. The Great Attractor marks the bottom of the valley, the deepest point where gravity is strongest. Galaxies throughout Laniakea are falling toward this valley, along paths determined by the slope of the gravitational potential. The steeper the slope, the faster the peculiar velocity. The gentler the slope, the slower the flow. This landscape metaphor is more than poetic. It is mathematically precise. The gravitational potential is a scalar field that assigns a value to every point in space. High values correspond to underdense regions where gravity is weak. Low values correspond to overdense regions where gravity is strong. The gradient of the potential, the rate at which it changes from point to point, determines the gravitational force and thus the acceleration of galaxies. Galaxies flow down the gradient from high potential to low potential, like water flowing downhill. The peculiar velocity field is directly related to the gradient of the potential. Measure the velocities and you can reconstruct the potential. Map the potential and you can identify basins and ridges. The Cosmic Flows team used this approach to define Laniakea. They identified the region where the gradient points inward, where galaxies are flowing toward a common center. The boundary is the surface where this gradient changes direction, where the flow switches from inward to outward. This is the gravitational divide, analogous to a continental divide in topography. On one side of a continental divide, rivers flow into one ocean. On the other side, rivers flow into a different ocean. Similarly, on one side of the Laniakea divide, galaxies flow toward the Great Attractor. On the other side, they flow toward neighbouring attractors like Perseus Pisces or Shapley. The Milky Way sits just inside the Laniakea divide, flowing inward along with the rest of the Virgo cluster. If you shifted our position outward by a few tens of millions of light years, we might cross the divide and belong to a different supercluster. The gravitational landscape is not smooth. It is lumpy and irregular, shaped by the distribution of dark matter. Dark matter dominates the mass of the universe, outnumbering ordinary matter by about 6 to 1. It does not emit or absorb light, making it invisible to telescopes, but it exerts gravity, and that gravity shapes the flows. Large concentrations of dark matter create deep valleys in the potential. Sparse regions create shallow slopes. The flows trace the dark matter distribution indirectly, allowing astronomers to map where the dark matter is located, even though they cannot see it directly. Within Laniakea, the landscape has multiple features. The Great Attractor is the primary valley, but it is not the only one. Smaller valleys correspond to rich galaxy clusters like Virgo, Hydra and Centaurus. These clusters are local minima in the gravitational potential, attracting nearby galaxies into their vicinity, but they are not isolated. They are all connected to the larger flow toward the Great Attractor, like tributary valleys feeding into a main valley. The ridges between basins are less well defined. They are not sharp boundaries, but gradual transitions where the gravitational pull from competing attractors balances out. Near a ridge, galaxies experience a weak net force because they are being pulled in different directions with roughly equal strength. Small changes in position or small variations in the mass distribution can shift which attractor dominates. Between the valleys are voids, regions where matter is scarce and gravity is weak. Voids do not attract galaxies. Instead, they act as repellers, pushing galaxies away toward the surrounding filaments and clusters. This might seem paradoxical. How can an empty region push anything? The answer lies in the gravitational imbalance. A galaxy inside a void experiences gravity from all directions. But because most of the matter lies outside the void in the surrounding walls, the net gravitational pull points outward toward the denser regions. The void is not pushing actively. The surrounding mass is pulling. And since the pull is strongest toward the outside, galaxies flow outward. The dipole repeller is a prominent void near Laniakea. It is located on the opposite side of the sky from the Great Attractor, roughly in the direction of the constellation Perseus. Galaxies in that region are flowing away from the dipole repeller and toward Laniakea and other nearby attractors. The combined effect of the Great Attractor pulling galaxies toward Laniakea and the dipole repeller pushing galaxies away from the opposite direction creates a strong dipole pattern in the local velocity field. This dipole contributes significantly to the Milky Way's peculiar velocity. We are falling toward the Great Attractor, but we are also being pushed away from the dipole repeller. The two effects reinforce each other, amplifying the overall flow. The gravitational landscape is dynamic. It evolves over time as matter redistributes. In the past, the landscape was smoother. Density contrasts were smaller, and valleys were shallower. As structure formed, valleys deepened and ridges sharpened. Galaxies that once flowed slowly now flow faster as they fall into increasingly deep potential wells. In the future, dark energy will reshape the landscape. Dark energy opposes gravity, working to flatten the potential and smooth out the valleys. On the scale of superclusters, dark energy is already strong enough to prevent gravitational collapse. Laniakea is not collapsing into the Great Attractor because dark energy pushes everything apart faster than gravity can pull it together. The valley exists and galaxies are falling into it, but the valley itself is expanding and will eventually dissolve. Billions of years from now, the gravitational landscape of the local universe will look very different. The deep valleys of today will have eroded into gentle slopes. The flows will have slowed or reversed. Galaxies that are now falling toward Laniakea will be drifting apart, carried by cosmic expansion into isolation. But for now, the landscape is well defined. Laniakea is a distinct basin of attraction, coherent structure in the gravitational potential, and we are flowing through it, carried by invisible currents toward the heart of our immeasurable heaven. Here is the unsettling truth about Laniakea. It is not permanent, unlike a galaxy or a galaxy cluster, which are bound together by gravity and will survive indefinitely. Laniakea is held together only temporarily by inward gravitational flows. Those flows are losing the battle against cosmic expansion. Follow-up studies have confirmed that Laniakea is not gravitationally bound and will disperse rather than maintain itself as an overdensity. Laniakea's fate, it appears, is dissolution. To understand why, we must examine the competition between gravity and dark energy. Gravity pulls matter together. It is an attractive force that causes galaxies to fall toward concentrations of mass. On small scales, gravity is strong enough to overcome cosmic expansion. Galaxies do not expand internally because their self-gravity binds them together. Galaxy groups and clusters are also gravitationally bound, meaning their internal gravity is sufficient to resist the expansion of space. The local group, for example, is gravitationally bound. The Milky Way and Andromeda will not drift apart. Instead, they will collide and merge in about 4 billion years. The Virgo cluster is also gravitationally bound. Its galaxies orbit a common center of mass, and the cluster will survive as a distinct entity for the indefinite future. But Laniakea is not bound. The supercluster as a whole does not have enough mass to keep itself together. Cosmic expansion, driven by dark energy, is pulling the structure apart faster than gravity can hold it together. Dark energy is a mysterious component that makes up about 68% of the universe's total energy density. It behaves opposite to normal matter. Where matter and radiation dilute as space expands, dark energy remains at constant density. Where matter attracts gravitationally, dark energy creates a repulsive effect that accelerates expansion. The exact nature of dark energy remains one of the biggest unsolved problems in physics. It might be a cosmological constant, an unchanging property of space itself. It might be a dynamic field that evolves over time. We do not know, but we can measure its effects, and those effects are profound. Dark energy began to dominate the universe's expansion about 6 billion years ago. Before that point, matter dominated, and gravity was slowing cosmic expansion. The universe was decelerating. After dark energy took over, expansion began to accelerate. Galaxies started to recede from each other faster and faster. This acceleration means that structures which are not gravitationally bound will be pulled apart. On the scale of superclusters, dark energy is already stronger than gravity. Laniakea is expanding along with the universe. The Great Attractor is receding from the Milky Way. The outer edges of the supercluster are receding even faster. Galaxies within Laniakea are falling toward the Great Attractor, but the Great Attractor itself is moving away from us due to cosmic expansion. It is like running toward a goal line that is retreating faster than you can run. You get closer to nearby competitors, but you never reach the finish line. The net result is that Laniakea is dispersing. The gravitational flows toward the center are real, but they are not sufficient to counteract the overall expansion. Over time, the flows will weaken as expansion carries galaxies apart and reduces the density contrasts. Eventually, the flows will reverse. Instead of falling toward the Great Attractor, galaxies will drift away from it. The basin of attraction will disappear. Laniakea will cease to exist as a coherent structure. This does not mean the galaxies will vanish. They will still be there, drifting through space, but they will no longer be connected by a common gravitational flow. The supercluster will have dissolved into isolated clusters and groups, each receding from the others at an ever-increasing rate. This fate is not unique to Laniakea. All superclusters will share the same end. The cosmic web itself is temporary. Filaments will break apart. Walls will fragment. Voids will expand to consume more and more of the universe. Only the densest structures, the galaxy clusters and groups, will remain as isolated islands in an ocean of expanding emptiness. The timescale for this dispersal is tens of billions of years. For now, Laniakea is intact and well defined. The flows toward the Great Attractor are strong and the structure is coherent, but it is living on borrowed time. This impermanence raises a philosophical question. If Laniakea is not gravitationally bound, is it a real structure? Some astronomers argue that the term supercluster should be reserved for structures that are gravitationally bound and will survive long term. By that definition, Laniakea is not a supercluster but merely a transient pattern in the velocity field, a temporary configuration that will not last. Others argue that the definition should focus on observable properties, not long-term fate. Laniakea is clearly a coherent structure in the present epoch. Galaxies within it share a common flow pattern and are gravitationally influenced by a common attractor. The fact that the structure will eventually disperse does not make it any less real today. The debate hinges on semantics, on how we choose to define our terms, but regardless of terminology, the physical reality is clear. Laniakea exists now as a distinct basin of attraction. It will not exist forever. We live in a moment of cosmic history when superclusters are prominent features of the universe, when the cosmic web is at its most dramatic. In the distant past, structure was subtler. In the distant future, structure will dissolve. We happen to live in the sweet spot when the universe is old enough to have developed rich structure, but young enough that dark energy has not yet erased it. Mapping Laniakea is not easy. Observing the cosmic web poses enormous challenges, and the Great Attractor region at the heart of Laniakea is particularly problematic. The main obstacle is the zone of avoidance. About 20% of the extragalactic sky is hidden behind the plane of the Milky Way, blocked by dust, gas, and the light of billions of stars. This zone happens to include the direction of the Great Attractor. We cannot see the central regions of our own supercluster with optical telescopes. The obscuration is severe. Dust absorbs and scatters visible light, dimming background galaxies by many magnitudes. In the densest parts of the galactic plane, extinction can exceed 30 magnitudes, meaning that light is reduced to 1/1,000,000th of its original intensity. No optical telescope can see through that. But astronomers are resourceful. They have developed strategies to peer through or around the zone of avoidance using different wavelengths of light. Infrared radiation penetrates dust better than visible light. Dust particles scatter short wavelengths efficiently, but allow longer infrared wavelengths to pass through with less attenuation. By observing in the near-infrared, astronomers can detect galaxies behind the galactic plane that are invisible optically. The 2-micron all-sky survey, or 2MASS, mapped the sky in the near-infrared and revealed thousands of galaxies in the zone of avoidance that were previously unknown. These observations helped fill in some of the gaps in our knowledge of the Great Attractor region. Radio observations are even more powerful. Radio waves are not affected by dust at all. They pass through the galactic plane as if it were transparent. Radio telescopes can observe neutral hydrogen gas in distant galaxies by detecting the 21 centimeter emission line. This line arises when the electron in a hydrogen atom flips its spin, releasing a photon with a wavelength of 21 centimeters in the radio part of the spectrum. Every galaxy contains hydrogen gas, and this emission is ubiquitous. By mapping 21 centimeter emission across the zone of avoidance, radio astronomers can detect galaxies and measure their velocities. The Parkes Observatory in Australia, equipped with a 64-meter radio telescope, conducted extensive surveys of the zone of avoidance in the 1990s and 2000s. These surveys discovered hundreds of galaxies hidden behind the Milky Way, including several galaxy clusters. One particularly important discovery was the Vela Supercluster, a massive structure located about 800 million light-years away in the direction of the Great Attractor. Vela was completely unknown before radio surveys revealed it, because the obscuration in that direction is so severe. More recently, the Meerkat radio telescope in South Africa has conducted detailed surveys of the Vela region. Meerkat is a cutting-edge instrument with 64 dishes working together as an interferometer, providing high sensitivity and resolution. The Meerkat surveys have detected hundreds of new galaxies in the zone of avoidance and are mapping the large-scale structure in unprecedented detail. These surveys reveal that the Vela Supercluster is even larger and more complex than initially thought, with multiple galaxy clusters and filaments hidden behind the Milky Way. X-ray observations also help. Hot gas in galaxy clusters emits X-rays, and X-rays can penetrate dust reasonably well. The Rosat satellite and later X-ray telescopes conducted surveys of the zone of avoidance looking for X-ray emission from clusters. These surveys identified the Norma cluster and confirmed its location near the centre of the Great Attractor region. Combining observations at multiple wavelengths gives a more complete picture. Infrared observations reveal the galaxies. Radio observations measure their distances and velocities through 10^1 centimeter redshifts. X-ray observations identify clusters and trace hot gas. Together, these data allow astronomers to map the hidden structures and understand how they fit into the larger context of Laniakea. But gaps remain. Even with multi-wavelength observations, some regions are still difficult to study. The very centre of the galactic plane, within a few degrees of the equator, is so obscured that even infrared and radio observations struggle to detect faint sources. Foreground stars confuse the picture, making it hard to distinguish background galaxies. Incompleteness biases affect surveys where only the brightest or most massive galaxies are detected, and fainter objects remain hidden. These limitations mean that our map of Laniakea is incomplete. We know the overall structure and the main components, we can trace the flows and define the boundaries, but the fine details, especially in the zone of avoidance, are uncertain. We do not know exactly how many galaxies are hidden there, or how much mass is obscured. Future observations will improve the situation. Next-generation radio telescopes like the Square Kilometre Array, currently under construction, will have unprecedented sensitivity and will be able to detect much fainter 21 centimeter emission. This will allow surveys to push deeper into the zone of avoidance and discover more galaxies. Space-based infrared telescopes avoid the atmospheric absorption that limits ground-based observations and can detect even fainter sources. The James Webb Space Telescope, launched in 2021, has capabilities that could contribute to mapping hidden structures, although its primary mission is focused on distant galaxies and the early universe rather than nearby structures. Combining data from multiple surveys will be crucial. The Cosmic Flows project continues to expand its catalogue of distance measurements, pushing to greater distances and including more galaxies. Each new release improves the reconstruction of the velocity field and refines the boundaries of superclusters. The latest Cosmic Flows 4 catalogue includes over 56,000 galaxies and extends the mapped region to about 1 billion light-years from Earth. This allows the team to study not just Laniakea, but also neighbouring superclusters and the flows between them. But even with the best observations, some uncertainty will always remain. We view the universe from one location, from inside the Milky Way. We cannot change our vantage point. The zone of avoidance will always be there, obscuring part of the sky. We can mitigate the problem with clever observing strategies and multi-wavelength data, but we cannot eliminate it entirely. This is the challenge of observational cosmology. We must piece together a picture of the universe from incomplete and biased data, using every tool at our disposal to fill in the gaps and test our models. The discovery of Laniakea and the larger structures around it has profound implications for cosmology. It tests our understanding of how the universe formed and evolved, and it raises questions about the validity of fundamental assumptions. One key implication concerns the cosmological principle. This principle states that the universe is homogeneous and isotropic on sufficiently large scales, meaning it looks the same everywhere and in all directions when averaged over large enough volumes. The principle simplifies cosmological models enormously. It allows us to describe the entire universe with a single, smooth metric and a few global parameters. But Laniakea challenges this principle. A structure 500 million light-years across is enormous, and if Laniakea is part of the even larger Shapley Concentration, the scale becomes incomprehensibly large. At what scale does the universe become homogeneous? If we find structures a billion light-years across, can we still claim the universe is uniform on scales of a few hundred million light-years? The standard answer is that homogeneity applies on scales of several hundred megaparsecs or more. Laniakea spans about a 60 megaparsecs, which is right at the edge of this range. Shapley extends farther. These structures do not necessarily violate the cosmological principle, but they push the boundaries. If even larger structures exist, or if Laniakea-like superclusters are common rather than rare, it would suggest the universe is more lumpy than the principle assumes. Simulations of structure formation based on the standard cosmological model, called lambda cold dark matter, or LCDM, predict a certain distribution of structure sizes. Small structures should be common, medium structures should be less common, very large structures should be rare. Laniakea and Shapley are at the large end of the predicted distribution. They are not impossible according to LCDM, but they are uncommon. The existence of multiple such structures in the observable universe could indicate that the model underestimates the formation of large structures. This could point to missing physics. Perhaps dark matter behaves differently than assumed. Perhaps dark energy has varied over time, affecting structure formation in ways not captured by current models. Perhaps the initial conditions after the Big Bang had more power on large scales than the standard inflation models predict. Distinguishing between these possibilities requires more data and more detailed simulations. Another implication concerns the Hubble constant, the parameter describing how fast the universe expands. Measurements of the Hubble constant from nearby supernova disagree with measurements from the cosmic microwave background by about 9%. This discrepancy is called the Hubble tension, and it is one of the biggest unsolved problems in cosmology. Laniakea might contribute to this tension. If we live inside a large underdense region, or near a particularly massive overdensity, our local measurements of the expansion rate could be biased. Peculiar velocities add to the cosmic expansion, making nearby galaxies appear to recede faster than they would in a perfectly smooth universe. Some researchers have proposed that the presence of Laniakea and Shapley biases our local Hubble constant measurements upward. The flows toward these structures add extra velocity to galaxies, inflating the apparent expansion rate. If this is correct, the true global Hubble constant might be closer to the value measured from the cosmic microwave background, and the tension might be partially or fully resolved by accounting for our local environment. However, other researchers argue that the effect is too small to fully explain the Hubble tension, or that the direction of the bias is uncertain. The debate remains active, and resolving it will require more precise distance measurements and a better understanding of the velocity field. Laniakea also provides a laboratory for studying dark energy. Dark energy dominates the expansion of the universe on large scales, but its effects are difficult to measure directly. By studying how superclusters like Laniakea evolve over time, astronomers can test models of dark energy and constrain its properties. If dark energy is a cosmological constant, its density remains constant as the universe expands. This leads to specific predictions about how structures grow and how quickly superclusters disperse. If dark energy varies in strength or has other properties, the predictions change. Comparing observations to models allows astronomers to rule out some dark energy models and support others. The dispersal of Laniakea, for example, provides a test. If the supercluster dissolves faster than predicted by a cosmological constant, it would suggest dark energy is stronger than assumed. If it dissolves more slowly, it might indicate dark energy is weaker, or that we underestimate the mass of the supercluster. Current observations are consistent with dark energy being a cosmological constant, but the uncertainties are still large. Future surveys will provide more stringent tests. Finally, Laniakea informs our understanding of galaxy formation and evolution. Galaxies do not form in isolation. They are influenced by their environment, by the flows of matter through filaments, by interactions with neighbouring galaxies, and by the gravitational potential of the supercluster. Galaxies in the central regions of Laniakea, near the Great Attractor, experience different conditions than galaxies on the outskirts like the Milky Way. Central galaxies are more likely to experience mergers, to accrete gas from filaments, and to be affected by the hot intracluster medium. These environmental effects shape galaxy properties, including their size, colour, star formation rate, and morphology. By studying galaxies across Laniakea and comparing them to galaxies in other superclusters, astronomers can disentangle the role of environment from intrinsic properties. This helps build a more complete picture of how galaxies form and evolve over cosmic time. Laniakea is not just an interesting structure. It is a crucial piece of the cosmic puzzle, informing multiple areas of cosmology and astrophysics. Understanding our home supercluster is essential to understanding the universe as a whole. Let me give you your complete cosmic address one more time. You live on a planet called Earth. Earth orbits a star called the Sun. The Sun is one of 200 billion stars in a spiral galaxy called the Milky Way. The Milky Way is one of about 80 galaxies in a gravitationally bound structure called the Local Group. The Local Group is part of a larger collection of galaxies called the Virgo cluster. The Virgo cluster is one component of an immense supercluster spanning 500 million light-years called Laniakea. and Laniakea appears to be part of an even larger structure centered on the Shapley Supercluster, which may extend across 1 billion light-years or more. This is your home in the immeasurable heaven. You are a droplet in a cosmic watershed, flowing along with 100,000 other galaxies toward a gravitational valley hidden behind the zone of avoidance. You are moving at over 2 million kilometers per hour, pulled by the combined gravity of thousands of galaxy clusters. You will never reach the destination because cosmic expansion is carrying it away faster than you can fall. But the journey continues nonetheless. The discovery of Laniakea is a milestone in our understanding of the universe. It represents a fundamental shift in how we define our cosmic neighborhood and our place within the larger structure. For most of human history, we thought we were at the center of everything. The Earth was the center of the cosmos, and the sun and stars revolved around us. Copernicus shattered that illusion. We are not at the center of the solar system. Then we learned we are not at the center of the galaxy. Then we learned the galaxy is not at the center of anything. Each discovery pushed us further from the center, made us smaller and less significant in the cosmic scheme. Laniakea continues that trend. We are not just residents of a galaxy or a cluster. We are residents of a vast basin of attraction, a structure so large that it contains everything we can see with our telescopes and still extends far beyond. And yet, even Laniakea is not unique. It is one of many superclusters scattered across the observable universe, all flowing through the cosmic web, all temporary structures held together by gravity against the relentless expansion of space. The story of Laniakea is also a story of human ingenuity and persistence. Mapping the cosmic web requires incredible dedication. Astronomers must measure the distances to thousands of galaxies using a variety of techniques, each with its own challenges. They must peer through the zone of avoidance using infrared, radio, and X-ray observations. They must develop sophisticated mathematical methods to reconstruct the velocity field from sparse and noisy data. The result is a map of the local universe showing where we are and where we are going. But the work is not complete. Many questions remain unanswered. How large is the Shapley concentration, and is Laniakea truly part of it? Are there even larger structures beyond Shapley? How do these structures affect our measurements of the Hubble constant and other cosmological parameters? What is the detailed distribution of dark matter within Laniakea? How did the supercluster form, and what will happen to it in the distant future? Future observations will address some of these questions. The Cosmic Flows project continues to expand, measuring distances to more galaxies and pushing to greater depths. New radio telescopes will map the zone of avoidance with unprecedented sensitivity. Advanced simulations will model structure formation in greater detail and test whether our observations match theoretical predictions. What is clear is that we live in an extraordinary time. The universe is 13.8 billion years old. For most of that time, structure was subtle. In the future, dark energy will erase structure, leaving isolated clusters drifting apart in an expanding void. We live in the brief window when the cosmic web is at its peak, when superclusters like Laniakea are well-defined and prominent. We are fortunate to exist in this epoch and to have developed the technology to map our place within it. Laniakea is our home in the most expansive sense. It is the largest structure we can claim to belong to, the boundary beyond which our gravitational connection to the universe fades. Understanding Laniakea gives us perspective. It shows us that we are part of something immense, something that dwarfs human scales of space and time. It also shows us that we are not special. The Milky Way is one galaxy among 100,000 in Laniakea, and Laniakea is one supercluster among many in the observable universe. We are ordinary, unremarkable, a tiny part of an incomprehensibly vast cosmos. And yet here we are, conscious beings living on a small planet capable of measuring the motions of galaxies hundreds of millions of light years away, capable of mapping the invisible flows of gravity that connect us to the rest of the universe. We can look up at the night sky and know that every star we see is flowing through Laniakea along with us, all of us carried by the same cosmic currents toward the same hidden attractor. That knowledge is both humbling and exhilarating. It reminds us of our insignificance and our potential. We are small, but we are not ignorant. We understand our place in the immeasurable heaven, and we continue to explore, to question, to map the universe with ever greater precision. The journey continues. Laniakea is our home, but it is also just one waypoint in a much larger exploration. Beyond Laniakea lie other superclusters, other basins of attraction, other structures waiting to be discovered. The cosmic web extends as far as we can see and beyond. Each new observation reveals more complexity, more connections, more wonders. If this journey through the immeasurable heaven has expanded your perspective, if you have gained a deeper appreciation for the scale and structure of the universe, then my work here is done. But your exploration does not have to end. The cosmos is full of mysteries waiting to be understood, and we will continue exploring them together. Hit that like button, subscribe, and join us as we navigate the cosmic ocean, charting the rivers of gravity that flow through the immeasurable heaven we call home. Thank you for watching, and remember, right now as you sit here, you are moving through space at over 2 million kilometers per hour, falling toward the great attractor at the heart of Laniakea, your home in the cosmos. The universe is vast, and you are part of it. Never forget that. The creation of the Cosmic Flows 2 catalogue represented years of painstaking work. Each galaxy in the catalogue required multiple observations using different techniques. For spiral galaxies, the team often used the Tully-Fisher relation, which connects a galaxy's rotation speed to its intrinsic luminosity. Spiral galaxies rotate because of the gravity of their stars and dark matter. Faster rotation means more mass, and more massive galaxies tend to be intrinsically brighter. By measuring how fast a galaxy rotates using spectroscopy, you can estimate how bright it should be intrinsically. Compare that to how bright it appears from Earth, and you can calculate its distance. For elliptical galaxies, which don't rotate the same way spirals do, the team used the fundamental plane relation. This connects 3 properties of elliptical galaxies: their size, their surface brightness, and their velocity dispersion, which measures how fast stars are moving randomly within the galaxy. These 3 properties are correlated in a specific way, and by measuring 2 of them, you can predict the third. This allows you to estimate the galaxy's intrinsic size, which combined with its apparent size, tells you its distance. The technique is similar in principle to the Tully-Fisher relation, but adapted for non-rotating systems. For the nearest and brightest galaxies, distance measurements using Cepheid variable stars provided crucial calibration. Cepheids are supergiant stars that pulse regularly, brightening and dimming with periods ranging from a few days to several months. The period of pulsation is tightly correlated with the star's intrinsic luminosity, a relationship discovered by Henrietta Leavitt in 1908. By observing the period, you know the luminosity. By comparing to the apparent brightness, you calculate the distance. The Hubble Space Telescope dedicated significant observing time to measuring Cepheids in nearby galaxies, providing anchor points for the cosmic distance ladder. Type Ia supernovae served as another crucial tool. These thermonuclear explosions occur when a white dwarf star accretes enough mass from a companion to exceed the Chandrasekhar limit of 1.4 solar masses. The white dwarf collapses and explodes, releasing a fairly consistent amount of energy. This makes Type Ia supernovae excellent standard candles. They're bright enough to see across hundreds of millions of light years, and after corrections for subtle variations in brightness related to explosion dynamics and dust extinction, they provide distance measurements accurate to about 10% or better. Combining all these techniques, the Cosmic Flows team built a 3-dimensional map of the local universe extending to about 300 million light-years. But distances alone were not enough. They also needed velocities. For each galaxy, they measured its redshift using spectroscopy, observing how the wavelengths of light from the galaxy are stretched by its motion. Redshift is easy to measure and provides the galaxy's line-of-sight velocity with high precision. But redshift includes both cosmic expansion and peculiar velocity mixed together. To separate them, the team used their distance measurements. Here's how it works. Hubble's law states that a galaxy's recession velocity due to cosmic expansion equals its distance times the Hubble constant. If you know the distance, you can calculate what the recession velocity should be. Subtract this from the total observed velocity from redshift, and what remains is the peculiar velocity, the galaxy's motion due to local gravitational effects. This calculation is straightforward in principle, but complicated in practice by various sources of uncertainty. Distance measurements have errors, typically 10 to 20%. The Hubble constant itself has some uncertainty, and peculiar velocities can be comparable to, or even larger than recession velocities for nearby galaxies. making the subtraction sensitive to errors. Despite these challenges, the Cosmic Flows 2 catalogue achieved unprecedented precision. For galaxies within about 100 million light-years, peculiar velocities could be measured with uncertainties of about 100 to 200 kilometers per second. This was good enough to trace flow patterns and map the gravitational field of the local universe. The team then used sophisticated reconstruction techniques to convert the sparse measurements of peculiar velocities at galaxy positions into a smooth three-dimensional velocity field filling all of space. The reconstruction process involved several mathematical steps. First, they assumed that the velocity field is caused by the gravitational pull of mass concentrations. This assumption is well founded in cosmology. Peculiar velocities arise from gravitational forces, or some sources, not from random motions. Second, they used linear perturbation theory, which describes how small deviations from perfect cosmic expansion evolve over time. In this theory, the velocity field is directly related to the gradient of the gravitational potential, which in turn is related to the density field. By measuring velocities, you can infer densities. Third, they applied a smoothing filter to the data, recognizing that individual galaxy velocities contain noise from measurement errors and random motions. Smoothing over scales of a few megaparsecs averages out these small-scale fluctuations and reveals the large-scale flow patterns. Finally, they used boundary conditions informed by observations beyond the survey volume to ensure the reconstruction didn't produce artifacts at the edges. The result was a complete three-dimensional velocity field, a map showing how galaxies are moving throughout the local universe. Streamlines could be traced through this field, following the flow of matter as it moves through space. And critically, surfaces could be identified where the flow changes direction, where galaxies stop flowing toward one attractor and start flowing toward another. The zone of avoidance is not a uniform blanket of obscuration. Its effects vary with direction and with wavelength. Near the galactic equator, where we look directly through the densest part of the Milky Way's disk, the extinction is severe, often exceeding 30 magnitudes in visible light. An extinction of 30 magnitudes means that light is dimmed by a factor of 1 trillion. A galaxy that would normally appear at magnitude 15, bright enough to see with a good amateur telescope there, would be dimmed to magnitude 45, far below the detection threshold of even the most sensitive instruments ever built. In these regions, optical astronomy is effectively impossible for observing external galaxies, but move away from the galactic equator toward higher galactic latitudes, and the extinction diminishes. At 10 or 20 degrees above or below the galactic plane, extinction might drop to a few magnitudes, still significant but not insurmountable. With deep exposures and infrared observations, galaxies can be detected. The zone of avoidance is therefore not an absolute boundary but a gradient, with the most severe obscuration concentrated in a band about 10 to 15 degrees wide, centered on the galactic equator. The Great Attractor, unfortunately, lies very close to this most obscured region, falling within about 5 degrees of the galactic plane. This places it in one of the worst possible locations for observation. The obscuration comes from multiple sources. Interstellar dust, consisting of tiny solid particles about a micron in size, absorbs and scatters light. Dust is most effective at blocking shorter wavelengths, which is why the Milky Way appears dark in optical images, but more transparent in infrared. The dust is not uniformly distributed, but concentrated in clouds and lanes, creating a patchy structure. Some lines of sight might have relatively little dust, while adjacent sight lines encounter dense clouds. This patchiness makes the zone of avoidance challenging to survey systematically. You cannot simply assume that all directions within the zone are equally obscured. Gas also contributes to the obscuration, though less dramatically than dust. Neutral hydrogen gas can absorb specific wavelengths of ultraviolet light, and ionized gas can scatter light. More importantly, the gas emits its own light, particularly in the form of H-alpha emission from excited hydrogen atoms. This emission, along with light from millions of foreground stars in the Milky Way, creates a bright background against which faint external galaxies are difficult to detect. Imagine trying to spot a distant lighthouse while standing in front of a stadium floodlight. The lighthouse is there, but the glare overwhelms your vision. Foreground stars are another major problem. The Milky Way's disk contains hundreds of billions of stars, and when you look through the disk, you see millions of these stars projected on the skid. Automated galaxy surveys rely on software to distinguish galaxies from stars based on their appearance. Galaxies are extended, showing up as fuzzy patches rather than point sources. Stars appear as sharp points, but when the field is crowded with stars, the software can become confused, mistaking groups of stars for a single extended object or failing to detect faint galaxies hidden among the stars. Human inspectors must carefully examine images to identify true galaxies, a time-consuming process. Despite these obstacles, astronomers have made progress piercing the zone of avoidance. Infrared observations at 2 microns, near infrared, reduce dust extinction by about a factor of 10 compared to visible light. The 2-micron all-sky survey, or 2MASS, conducted in the late 1990s and early 2000s, used infrared-sensitive detectors to map the entire sky, including the zone of avoidance. The survey detected hundreds of thousands of galaxies, including many in regions too obscured for optical observations. 2MASS allowed astronomers to map the distribution of galaxies behind the Milky Way and confirm that structures like the Anomaly cluster exist. Radio observations provide even better penetration. Radio waves with wavelengths measured in centimeters pass through dust essentially unimpeded. Radio telescopes can observe neutral hydrogen gas in galaxies by detecting the 21-centimeter emission line, a spectral feature produced when the electron in a hydrogen atom flips its spin state. Every galaxy contains hydrogen gas, and this emission is ubiquitous. By tuning a radio telescope to frequencies around 1420 MHz, corresponding to 21 centimeters, astronomers can detect galaxies and measure their velocities through the Doppler shift of the emission line. The advantage of radio observations is that they are unaffected by dust. The disadvantage is that radio telescopes typically have poorer angular resolution than optical telescopes, making it harder to pinpoint exactly where a galaxy is located on the sky. Interferometry using arrays of radio telescopes working together helps improve resolution, but the technique requires sophisticated data processing. X-ray observations also contribute. Hot gas in galaxy clusters emits X-rays, and X-rays can penetrate dust reasonably well. The Rosat satellite, which operated in the 90s, conducted an all-sky X-ray survey and detected emission from the Anomaly cluster, confirming its location near the center of the Great Attractor region. Subsequent X-ray observatories, including XMM Newton and Chandra, have observed the cluster in greater detail, mapping the temperature and density of the hot intra-cluster medium and measuring the cluster's mass from X-ray observations. The hierarchical nature of cosmic structure, where superclusters nest within larger superclusters, is both fascinating and troubling for cosmology. It raises profound questions about the nature of the universe and the limits of our ability to understand it from our single vantage point. One of the central assumptions of modern cosmology is the cosmological principle, which states that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means it looks the same everywhere. No location is special. Isotropic means it looks the same in all directions. These assumptions are not just convenient simplifications, they are foundational to our cosmological models. The Friedmann equations, which describe the expansion of the universe in the context of general relativity, assume homogeneity and isotropy. They allow us to model the entire cosmos with a single metric, a mathematical description of space-time curvature that applies everywhere. Without these assumptions, the equations become vastly more complicated. We would need to account for variations in density and expansion rate from place to place, tracking how each region evolves differently. The models would become mathematically intractable, and making predictions would be nearly impossible. The cosmological principle has been remarkably successful. Observations of the cosmic microwave background radiation show that the universe was nearly perfectly uniform around 80,000 years after the Big Bang, with density variations of only about 1 part in 100,000. This uniformity extends across the entire observable universe, supporting the idea that no place is special. Large-scale galaxy surveys show that when you average over scales of several 100 million light-years, the distribution of galaxies becomes increasingly uniform. Local fluctuations smooth out, and the universe appears homogeneous, just as the principle requires. But Laniakea and Shapley challenge this comfortable picture. A structure 500 million light-years across is enormous. Even averaging over such a large scale, we still see significant structure. And if Shapley extends to 1 billion light-years or more, encompassing multiple superclusters including Laniakea, the scale of structure approaches the size of the observable universe itself. At what point can we claim the universe is homogeneous? If we find structures comparable to the Hubble radius, the maximum distance light could have travelled since the Big Bang, we face a serious problem. The cosmological principle might not hold, or it might hold only on scales so large that we cannot observe enough volume to verify it. Some cosmologists argue that Laniakea and Shapley do not violate the cosmological principle because they are not gravitationally bound structures. They are basins of attraction, regions where galaxies happen to be flowing toward a common centre due to local gravitational imbalances. But these flows are temporary, artifacts of the particular configuration of density fluctuations that existed in the early universe. Over time, dark energy will disperse the structures, and the universe will become more homogeneous. In this view, we live in a special epoch when structure is at its peak, when the cosmic web is clearly visible. In the distant past, structure was subtler. In the distant future, structure will fade. The cosmological principle applies on average over time, even if it seems violated at any given moment. Other cosmologists are less sanguine. They point out that if we observe structures that are statistically unlikely according to our models, we should take that seriously. Either we are incredibly lucky to live in an unusual region of the universe, which seems to violate the spirit of the cosmological principle, or our models are wrong and structure formation proceeds differently than we think. The latter possibility is troubling because it would require rethinking fundamental aspects of cosmology, perhaps revising our understanding of dark matter, dark energy, or gravity itself. The universe is vast beyond comprehension. Numbers fail to capture the scale. Analogies fall short. We speak of billions of light years, of hundreds of thousands of galaxies, of masses equivalent to 100 million billion suns. But these are just words. They do not convey the visceral reality of the abyss of space, the incomprehensible distances separating one galaxy from another, the unimaginable duration of cosmic time. And yet, here we are, conscious beings on a small planet capable of measuring and mapping this vastness, capable of understanding our place within structures so large they dwarf everything our ancestors could have imagined. The discovery of Laniakea is more than just a scientific achievement. It is a cultural milestone, a marker in humanity's long journey toward understanding the cosmos. For thousands of years, we thought Earth was the centre of everything. The sun, moon, planets, and stars all revolved around us. This geocentric view felt intuitively correct. We are here, after all, and everything seems to move around us. But Copernicus shattered that illusion. Earth orbits the sun, not the other way around. We are not at the centre of the solar system. That was humbling, but it was just the beginning. Then we learned we are not at the centre of the galaxy. The sun is just one star among billions, located in a nondescript region of a spiral arm about 2/3 of the way from the galactic centre. Our galaxy is not even at the centre of the local group. Andromeda is more massive, and the local group is not at the centre of Virgo. It sits on the outskirts. Each discovery pushed us further from the centre, made us smaller and less significant in the cosmic scheme. The history of modern astronomy is a history of decentering, of progressively removing humans from any special cosmic position. Laniakea continues that trend with a vengeance. We are not just residents of a galaxy or a cluster. We are residents of a vast supercluster, and we sit near its edge, far from the gravitational heart. And Laniakea itself may be just one component of an even larger structure centered on Shapley. We are pushed to the periphery again and again, each new discovery revealing that what we thought was the center is actually just another suburb, another outlying region of something much bigger. The universe does not care about us. It did not arrange itself for our benefit or put us in a special location. We are ordinary, unremarkable, living in an ordinary galaxy in an ordinary part of an ordinary supercluster in what appears to be a fairly typical region of the universe. And yet, there is something extraordinary about us. We are conscious. We can observe. We can think. We can measure the motion of galaxies hundreds of millions of light years away and reconstruct the invisible flows of gravity that connect us to the rest of the cosmos. We can look up at the night sky and know that every star we see is flowing through Laniakea, along with us. All of us carried by the same currents toward the same hidden attractor. That knowledge is both humbling and empowering. It shows us our place, small and insignificant, but it also shows us our potential, vast and unbounded. The work of mapping Laniakea is not finished. The Cosmic Flows project continues, with new catalogues pushing to greater distances and including more galaxies. Cosmic Flows 4, published in 2003, contains over 56,000 galaxies and extends the mapped region to about 1 billion light-years. This allows astronomers to study not just Laniakea, but also neighbouring superclusters and the flows between them. Future versions will push even farther, mapping a larger and larger volume of the observable universe. Each new release refines our understanding of cosmic structure and tests our theories against observation. New telescopes will contribute to this effort. The Square Kilometre Array, currently under construction in South Africa and Australia, will be the most powerful radio telescope ever built. It will detect neutral hydrogen emission from billions of galaxies, mapping the cosmic web in unprecedented detail. The Vera Rubin Observatory, which began operations in 2024, conducts a decade-long survey of the entire visible sky, imaging billions of galaxies and measuring their positions and colours. The James Webb Space Telescope, launched in 2021, observes the infrared universe with exquisite sensitivity, revealing galaxies too faint or too obscured for previous telescopes. These instruments will answer many questions about Laniakea. How precisely can we define its boundaries? How does its mass distribution compare to theoretical predictions? What is the detailed structure of the Great Attractor region, and how much mass is hidden in the zone of avoidance? How does Laniakea connect to neighbouring superclusters, and what are the flow patterns between them? Is there evidence for structures even larger than Shapley? These are concrete, answerable questions that will be addressed over the coming decade. But perhaps the most profound question is philosophical. What does it mean to live in Laniakea? What does it mean to know that we are part of something so vast, so ancient, so indifferent to our existence? For some, this knowledge is existentially terrifying. It reveals our cosmic insignificance, our ultimate powerlessness against the forces of nature and the passage of time. We are ephemeral creatures on a fragile planet, adrift in an immense and uncaring universe. Nothing we do matters on cosmic scales. Our entire civilization, all of human history, all of our achievements and failures are less than a blink of an eye in cosmic time, less than a speck of dust in cosmic space. For others, this knowledge is liberating. If nothing matters cosmically, then we are free to create our own meaning, to decide for ourselves what is important and what is worth pursuing. We are not bound by cosmic destiny or divine plan. We are free agents, conscious beings capable of choice and creativity. And in that freedom lies immense possibility. We can explore. We can create, we can build civilizations and tell stories and make art and love each other. We can look up at the night sky and marvel at the beauty and the mystery. We can dedicate ourselves to understanding the cosmos, to mapping its structure and uncovering its secrets, not because it will change anything on cosmic scales, but because it enriches our lives here and now. The measurement of peculiar velocities represents one of the most challenging tasks in observational cosmology. Unlike measuring redshifts, which is straightforward and can be done with high precision using modern spectrographs, measuring distances requires significant telescope time and careful calibration. Consider the Tully-Fisher relation, one of the workhorses of distance measurement for spiral galaxies. To apply this relation, you need to measure the galaxy's rotation velocity, which requires obtaining a spectrum with sufficient signal-to-noise ratio to detect the galaxy's emission lines clearly. For nearby bright galaxies, this might take only a few minutes of telescope time. For distant or faint galaxies, it might require hours of integration to accumulate enough photons. The rotation velocity must be corrected for the galaxy's inclination angle, how tilted it is relative to our line of sight. A galaxy seen face-on shows little Doppler shift from rotation because we're looking perpendicular to the rotation axis. A galaxy seen edge-on shows maximum Doppler shift. To get the true rotation velocity, you need to measure the inclination from the galaxy's shape. But dust extinction, spiral structure, and other factors can make this measurement uncertain. Errors in inclination translate directly into errors in the inferred distance, and these errors are not always easy to quantify. Then there's the issue of the Tully-Fisher relation itself. The relation is not perfectly tight. There is scatter, meaning galaxies of the same rotation velocity can have somewhat different intrinsic luminosities. This scatter introduces an irreducible uncertainty in distance measurements. Moreover, the relation must be calibrated using galaxies with independently measured distances, typically from Cepheid variables or other methods. The calibration introduces its own uncertainties, which propagate into all subsequent distance measurements. The result is that even under the best circumstances, Tully-Fisher distances have uncertainties of 15 to 20%. For elliptical galaxies, the fundamental plane method faces similar challenges. You need to measure the galaxy's effective radius, its average surface brightness within that radius, and its velocity dispersion. Each measurement has its own sources of error. The effective radius depends on fitting a model to the galaxy's light profile, which can be complicated by mergers, dust lanes, or other irregularities. The surface brightness must be corrected for dust extinction, both in the Milky Way and in the target galaxy itself. The velocity dispersion requires a high-quality spectrum with sufficient resolution to resolve the broadening of spectral lines caused by the random motions of stars within the galaxy. All these complications mean that compiling a catalogue of thousands of distance measurements, as the Cosmic Flows team did, represents an extraordinary investment of observing time across multiple telescopes worldwide. The team used data from numerous facilities including the Hubble Space Telescope, the Spitzer Space Telescope, ground-based observatories in Hawaii, Chile, and Arizona, and radio telescopes for measuring neutral hydrogen. They combined archival data from past surveys with new observations targeted specifically at galaxies important for mapping the velocity field. The entire effort spanned more than a decade and involved hundreds of collaborators. The dispersal of Laniakea over cosmic time is not just a theoretical prediction, but something we can model in detail using computer simulations. Cosmologists run simulations that follow the evolution of the universe from the Big Bang to the present and beyond, tracking how dark matter and normal matter respond to gravity and cosmic expansion under our current understanding of physics. These simulations, with names like Illustris, Eagle, and Millennium, employ sophisticated numerical techniques to solve Einstein's field equations and the equations of hydrodynamics on millions of computational elements. In these simulations, Laniakea-like structures appear naturally as gravity amplifies initial density fluctuations. In the early universe, simulated at redshifts of 10 or 20, corresponding to times a few hundred million years after the Big Bang, the density field is relatively smooth. Small fluctuations exist, but they're subtle. Over time, gravity pulls matter into the densest regions, creating filaments and nodes. By redshift 1, about 7.7 billion years ago, when the universe was roughly half its current age, the cosmic web is already well developed, with clear filaments connecting rich galaxy clusters. At redshift 0, the present day, the simulations show superclusters like Laniakea at their peak prominence. The structures are well defined, with strong inward flows towards central attractors. Galaxies are falling into clusters at hundreds of kilometers per second. The contrast between filaments and voids is maximal. But if you run the simulations forward in time, continuing into the future based on our current understanding of dark energy, the structures begin to fade. By a redshift of 0.5, corresponding to a timeable about 8 billion years in the future when the universe will be roughly 22 billion years old, the expansion has carried clusters apart if dark energy continues behaving as observations suggest. The flows have weakened, some structures have dispersed entirely, with galaxies that once flowed together now receding from each other. By a redshift of 1, roughly 13 billion years in the future, the cosmic web has largely dissolved. Only the densest clusters remain as gravitationally bound islands, separated by ever-expanding voids. Laniakea no longer exists as a coherent structure. The Great Attractor, the gravitational heart of the supercluster, still contains its tight cluster of galaxies. The Norma cluster, Centaurus and Hydra remain, each cluster surviving as an isolated entity, but the connections between them have been severed by expansion. The Virgo cluster, once linked to these clusters by gravitational flows, has become unreachable, separated by billions of light years of expanding space. In the very distant future, tens of trillions of years hence, if current cosmological models hold, even the clusters will begin to dissolve. Galaxies will evaporate from clusters as close gravitational encounters fling some galaxies to high velocities, causing them to escape. Other galaxies will sink toward the cluster center, merging into a single supergiant galaxy. Based on our understanding of gravitational dynamics, each cluster would either evaporate entirely or collapse into a single remnant. and those remnants would drift alone through an ever-expanding universe, isolated by such vast distances that light from one remnant would never reach another. The cosmic web, the largest structure in the universe today, would be forgotten, its traces erased by the relentless expansion of space. These predictions, of course, depend on dark energy continuing to behave as we currently observe it, which remains one of the great unknowns in cosmology. The future of mapping Laniakea and understanding its place in the cosmic web depends critically on next-generation observatories. Several major facilities now under construction or in planning will revolutionize our ability to study large-scale structure. The Square Kilometre Array, or SKE, will be the world's largest radio telescope, with a collecting area of 1 square kilometre distributed across thousands of individual antennas. Phase 1 of the SKA is being built in 2 locations: SKA Mid in South Africa, consisting of nearly 200 dishes observing at frequencies from 350 MHz to 15.4 GHz, and SKA Low in Australia, consisting of 13172 individual antennas observing from 50 to 350 MHz. The SKA will detect the 21 cm line from neutral hydrogen in billions of galaxies extending to redshifts beyond 1, allowing the construction of 3-dimensional maps of the cosmic web across half the age of the universe. These maps will trace how superclusters formed and evolved over time, testing theoretical models of structure formation and dark energy. The SKA's sensitivity will also allow detection of galaxies in the zone of avoidance that are too faint for current telescopes, finally revealing the full extent of structures like the Vela Supercluster. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope or LSST, began operations in 2014 from its location on Cerro Pachón in Chile. Its 8.4-meter primary mirror and enormous field of view allow it to image the entire visible sky every few nights, detecting changes and transient events. Over a planned 10-year survey, Rubin will observe billions of galaxies, measuring their positions, colours and shapes. The survey will discover countless new galaxy clusters, map the dark matter distribution through gravitational lensing, and track the motions of galaxies over time. The European Space Agency's Euclid mission, launched in 2023, observes the universe in visible and near-infrared wavelengths from a vantage point at the Sun-Earth Lagrange Point 2, about 1.5 million kilometers from Earth. Euclid's wide-field imaging will map the shapes of billions of galaxies, measuring gravitational lensing effects that trace the distribution of dark matter. Its spectroscopic survey will measure redshifts for tens of millions of galaxies, allowing 3-dimensional mapping of large-scale structure. Euclid's data will complement ground-based surveys like Rubin, providing a space-based perspective free from atmospheric distortions. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will conduct infrared surveys of unprecedented depth and area. Roman's 2.4-meter primary mirror, the same size as Hubble's, will be equipped with modern infrared detectors and a wide-field instrument covering 200 times the area of Hubble's field of view. Roman will map hundreds of millions of galaxies, measuring their distances through multiple techniques including Type A supernovae and baryon acoustic oscillations. The mission will provide crucial data on dark energy's properties and the expansion history of the universe. These missions will work synergistically, each contributing unique data that combines to create a comprehensive picture of cosmic structure. Ground-based optical surveys like Rubin will detect the faintest galaxies and track time-variable phenomena. Space-based infrared missions like Roman will penetrate dust and observe the most distant galaxies. Radio surveys like SKA will map neutral hydrogen and trace structure formation. Together, they will allow astronomers to map Laniakea and its neighbours in exquisite detail, tracking galaxy flows with unprecedented precision and extending the mapped volume to encompass a significant fraction of the observable universe. The combination of these surveys will also allow definitive tests of competing theories. If modified gravity theories are correct, the enhanced structure formation they predict will show up clearly in maps of the cosmic web at high redshift, if the standard lambda cold dark matter model is correct. The observations should match its predictions. Either way, the next decade will settle long-standing debates and either confirm our current understanding or force a revolution in cosmological theory. As we conclude this journey through Laniakea, our home in the immeasurable heaven, let us reflect on what we have learned and what remains to be discovered. We have traced our cosmic address from Earth through an expanding hierarchy of structures, each one larger and more encompassing than the last. From planet to solar system to galaxy to local group to Virgo cluster to Laniakea Supercluster, and possibly beyond to the Shapley Concentration, each step has revealed new wonders and new mysteries. We have learned that the universe is organized on scales that dwarf human comprehension, with galaxies flowing through space like rivers through a landscape, following invisible currents of gravity toward attractors we can barely perceive. We have discovered that we live in a cosmic web, a vast network of filaments and clusters surrounding enormous voids, a structure that formed over billions of years as gravity amplified tiny quantum fluctuations from the infant universe into the largest architecture in nature. We have found that our supercluster Laniakea is defined not by where its galaxies are, but by where they are going, by the coherent flows that carry them toward the great attractor hidden behind the zone of avoidance. We have learned that Laniakea is not permanent but temporary, held together for a brief cosmic moment before dark energy tears it apart and leaves only isolated clusters drifting through an ever-expanding void. And we have confronted our cosmic insignificance. We are tiny creatures on a small planet in an ordinary galaxy, on the outskirts of a supercluster that is itself just one among many. The universe does not care about us. It did not make us special. We are products of natural processes, of physics and chemistry and evolution, remarkable in our complexity but unremarkable in our location. There is no cosmic center, no special place, no destination toward which everything flows. There is only structure and expansion, gravity and dark energy, matter and space playing out their eternal dance across trillions of years and trillions of light years. But in this insignificance lies a kind of freedom. We are not constrained by cosmic destiny. We are free to make our own meaning, to decide what matters and what we care about. And what we have chosen to care about is understanding. We have chosen to look up at the night sky and ask why, to build telescopes and measure distances, to map the invisible and comprehend the incomprehensible. This is our nature as conscious beings. We explore not because it will change anything on cosmic scales, but because exploration enriches us, because knowledge brings joy, because understanding connects us to the universe in ways that transcend our physical insignificance. The story of Laniakea is far from over. Every observation opens new questions. How did such large structures form? What role does dark matter play in their evolution? How does dark energy work, and will it continue to accelerate expansion indefinitely? Are there structures even larger than Shapley? What does it mean for our cosmological models if the universe is more lumpy and hierarchical than the cosmological principle allows? These questions will occupy astronomers for decades to come, driving the construction of new telescopes, the development of new techniques, and the refinement of theoretical models. And perhaps, someday, other questions will arise that we cannot yet imagine. Science progresses not just by answering questions, but by discovering new questions to ask. Each answer reveals deeper mysteries. Each solution opens new problems. This is not a flaw of science, but its greatest strength. We never reach final truth, only better and better approximations. We never complete the map, only fill in more details. The universe is vast and complex, and our understanding will always be partial and provisional, but it will also always be growing, always improving, always bringing us closer to comprehending our place in the cosmos. If this journey through Laniakea has changed how you see the universe, if you now look up at the night sky with new understanding and new wonder, then I have succeeded. You now know your cosmic address. You now understand that you are part of something immense, something ancient, something beautiful and terrible and utterly indifferent to your existence. You are a resident of the immeasurable heaven, flowing through space at over 2 million kilometers per hour toward the great attractor, carried by currents of gravity you cannot see, part of a structure so vast it contains everything you can observe and more besides. Remember this knowledge, carry it with you. Let it humble you when you feel important, and let it empower you when you feel small. You're tiny, but you are aware. You're insignificant, but you can understand. You're temporary, but you are part of something eternal. You are Laniakea. Your immeasurable heaven, your home. Thank you for watching. If this video expanded your perspective, if you gained a deeper appreciation for the scale and structure of the universe, hit that like button and subscribe for more explorations of the cosmos. We have many more wonders to discover together, many more mysteries to unravel. The universe is vast, and we have only begun to explore it. And remember, right now, as you finish reading this, you are moving through space at over 2 million kilometers per hour. You are falling toward the great attractor at the heart of Laniakea. You are part of the cosmic web, flowing with 100,000 other galaxies through the immeasurable heaven we call home. The universe is vast, incomprehensibly vast, and you're part of it. Never forget that. Until next time, keep looking up, keep questioning, keep exploring. The cosmos awaits.